Hi guys, this is Pallav. Today I'm going to teach you how words are turned into numbers. So, as you all know, this is, let's say, a computer. Okay. And how does a computer understand a word like cat or a word like apple? It doesn't speak English, it speaks numbers, that is binary, zeros and ones. So, how does it understand a cat or an apple? How do we turn words, which are messy, emotional, human words, into something that a machine can understand? Let's find out. Okay, let's say I have a list of words. Let's say I have cat, apple, banana, and a dog. Okay, now the simplest way to represent them in such a way that they are binary and help computer understand is by simply representing them as a binary vector with just zeros and ones. So let's say in order to understand what a cat is, I'll just write it as 1, 0, 0, 0. So this entire vector will represent what in turn a cat is. Okay, now moving on. It could be either way. It doesn't really matter with the order. It's just that when this specific value in the vector is 1, it denotes a dog. If this one, that is the second term, is 1, then it represents a banana. It's as simple as that. But with this, we find an issue. First issue would be fitting this data. As we know, our vocabulary is really vast. So fitting all this data into a small computer would be too big of a deal. And second, these are just IDs with no meaning in them. For example, let's consider apple here. Apple is as different to banana as it is to cat. There is no sense of similarity to make any sense out of the words. So how do we combat that particular defect? Not a defect exactly, we can call it a detriment, disadvantage, or a drawback of one hot encoder. So this entire process is actually called one hot encoding. Okay, now let's move on to understand how do we have a sense of similarity and give these words a meaning. Okay, so on the basis of what we just learned right now, if we try to plot all these 4 points on a 2D plot, there'll be something like this. This will be apple, this will be cat, this will be banana, and this will be dog. Or somewhere scattered. It doesn't necessarily have to follow this particular pattern. Let's say they are like this. As we can see, there is no particular relation between these 2 points. That's to say, we have no relations between any 2 points, which actually should be related, since cats and dogs are, as we know, both animals, whereas banana and apple are fruits. So how do we combat that? Okay, let's say we have a 2D plot again, and our y-axis represents animalness. That is some abstract parameter that represents what it is being an animal. Okay, and let's say our x-axis represents fruitness, some abstract parameter that represents what it's being a fruit. So, what if we could point out an apple and a banana that'll be close to this side? So we are able to group them together, and compared to, let's say, the animals, a cat and a dog, and help group them together. So scientists came up with a brilliant thing, which are called vector embeddings. Now let's try to learn what vector embeddings actually do and how are they different from one hot encoding. Okay, so what a problem statement basically led us to was basically understanding what is the meaning of a word and how do we translate it to geometry. Or it could be the other way around. How does geometry help us derive the meaning out of a word? So in order to do that, let's assume we have a vector database where each row represents a word. That was a cat, an apple, a dog, or a banana. Now we assign these cats, dogs, apples a value. Right now, you need to keep in mind that all these values are random, and I just picked them up because, well, I like these values. Okay, so these are random values. We understand that. So a computer also works in the same way. A model will basically assign random values to cats, apples, and dogs. And then what it does is basically it'll run simulations for different values of this column, different values for this column, and there might be more columns also. Does not necessarily have two values, but since we are trying to represent them in a 2D plane, I've tried to come up with two values only. Okay, so they might have essentially have more columns. So each row represents a word, whereas columns represent like extra parameters, you could say. Basically, fine tuning. The more columns that we have, the more precise the model will be, allowing you to have better vector embeddings for each one. And the less columns you have, the lower the precision will be. Okay, so what did we learn? We learned that for each row that we have, we'll have words. So each word would represent one row in this embedding space. And for each column, it basically offers more precision or a better vector embedding table that allow us to have more accurate embedding vectors for each word, or basically help it to be more precise in nature. So we then train the model, and after training the model would come up with values, and these values would be something similar to this. Okay, so these are the values that will be outputted or something similar to this after the model is done training. And this essentially would look something like this on a vector embedding space. Okay, now if we try to represent the values that we just found out on a 2D plane that we agreed upon, that was x-axis for fruitness, y-axis for animalness, and each point here represents will be something like this for dog, this for cat, this for apple, and this for banana. So okay, so you can see geometrically this will be the dog vector, this will be the cat vector, and this will be the apple vector. So first of all, visually, we can see that a dog is quite close to a cat, an apple is quite close to a banana. This is how they should be, theoretically, since they are related to each other, since apple is a fruit, banana is also a fruit. So this represents how similar they are because they're grouped together, closer to each other. Whereas we also find out how dissimilar each different word is. An apple is quite dissimilar to a cat. It's supposed to be different because they are animals and these are fruits. And how do we find this? Geometrically, we can't just say these points are closer, so obviously. We need to find out a number for them. So the number that we use is basically the angle between. So angle between each vector allows us to understand the similarity between each of them. So this is how we can represent the vector embeddings or the word embeddings that we just found out by training our model from a bunch of random numbers and then representing them here on what we call and embedding space. Okay, so what did we learn today? We started off with a simple word that was cat. We learned how to convert them into one-hot encoding, that is assigning them a binary vector, so one-hot encoding, and then we moved on to learning them on how to convert them into vector embedding, that is to say some random value like this, and this offers it a sense of semantic value or a meaning to it. So this is how we converted words into something the computer can understand, which is numbers. But you might think, how do words that actually make up a sentence give meaning to a computer? Because word sentences aren't just a group of words, but they actually have a meaning assigned to them. So how does a computer understand this?
Okay, so how do we make sense out of sentences? In order to understand this, we'll also have to understand how models are actually calibrated in order to find out the vector embeddings. We'll learn about this and more in the upcoming videos. Thank you. Good night.